right. Thank you for your patience there. Here we go, though. So we'll call this more techniques for evaluating limits. I am, but if you don't want to, you don't have to. I will eventually get to the paper, though, on the graph side. So if you want to do it on the back, you can. Just save, just so you reuse this. Or if you want to do it on your own paper in your notebook, that's fine with me. It doesn't matter. If you want to cut the graph out, do I have scissors over here? I have some scissors. So if you want to cut the graph out and tape it into your notes, that's fine too. I've got scissors. I can get tape too. So it's your choice. If you want to put it in your own, notebook or something like that, we can accommodate that. Okay. So let me know. But either way. More techniques for evaluating limits here today. That's what we're talking about. All right. We're going to continue on. So again, remember there are three kind of major ways that we evaluate limits. Okay. The very first way that we looked at was using a table, right? And so that's kind of like a numeric approach. We just plug in numbers. They get closer and closer to whatever x value we're approaching, both from the left-hand side of that x value and from the right-hand side of that x value, right? Both from values that are, in other words, less than that x value and from values that are greater than that x value, getting closer and closer. Okay, that was like that numeric method. Then we also talked about the graphing. We're going to look at graphing later today, and then we also talked about analytic, right? And the analytic way is basically kind of like doing stuff with the function. So the primary way we do that is direct substitution. Or if direct substitution doesn't work, we try factoring, canceling, and then direct substituting, right? So another method we're going to look at today for that analytic method to kind of fall under that umbrella is something I'm going to just call rationalization. Okay, and you'll see here. So our example, we'll show it to you through an example. So let's say we want to evaluate the limit. Okay, as our directions here. And let's say that our limit is as x approaches 0, okay, of the square root of x plus 1 minus 1 all over x. Okay. So if we try a direct substitution at this point, what will result? Okay, not just dividing by 0, we'll also get 0 in the numerator as well, right? We'll get 0 plus 1, which is 1. Square root of 1 is 1. Minus 1 will be 0. So if we try direct substitution, we get 0 plus 1 minus 1 over 0, which is 0 over 0, indeterminate. Okay? And when it comes to indeterminate form, again, indeterminate means it's not determined, it's undetermined what exactly is happening here, right? We don't know. We saw with, for example, number 3 from the warm-up, the one that Rohan showed us, right? That if we did a direct substitution right away, we got 0 over 0. That didn't, indeterminate form, but then we were able to factor and cancel and get 6/5. Okay, so indeterminate form there led to 6/5. But for number 4, right, when we did that one, also direct substitution led to 0 over 0. Okay, as Jenna did, but and she correctly identified that means the limit does not exist. Okay, but of course we had to give a little more explanation behind just that. Okay, so sometimes, right, indeterminate form leads to still a limit, right? But sometimes indeterminate form leads to not existing. All right, so we want to be careful there and we don't know. Okay, we don't know what it means. That's why it's indeterminate. Okay, so what other methods do we have here? Well, we can use our graphing calculators, right? So let's see if we can use our graphing calculators here to figure it out. So go ahead, use your graphing calculator and see if you can figure out what this limit's going to be. Okay, make sure you type it into your y equals accurately, right? Remember, we are approaching 0, and to give a good analysis, you need to make sure you're approaching 0 both from values that are less than 0, so in this case negative numbers, right, and from values greater than 0, in this case positive numbers, right? You don't have to do a full-fledged table on your paper if you don't want to, but yeah. See what you can come up with there. But again, make sure you check both sides of 0. seconds here to get that figured out. Okay, so what do we say here? What is this limit? If we use our table on our graphing calculator, what is it? What does it look like it's approaching? What do we say there? The limit is x approaches 0 of root x plus 1 minus 1 all over x is, looks like it's equal to 0.5. Thank you. Or 1/2. So it looks like we do have a limit here. But if we try direct substitution, we get 0 over 0. And can we like factor and cancel this? Not really, right? Yeah, it's not really a polynomial with that square root in there. So I'm going to show you what we're going to do. Okay, we're going to rationalize this thing, right? So if you remember that technique from, big back in algebra 2 when you had to, like rationalize denominators and stuff like that, okay? Or if you took if you had like imaginary numbers in your denominator and you have to multiply by the conjugate, same idea here, okay? Except in this case, because our square root, right, is in the numerator, we're going to multiply by the conjugate of the numerator here, okay? So in other words, multiply by root x plus 1 plus 1 over root x plus 1 plus 1. Okay? And we do that to create a difference of squares, right? To create a difference of squares here in the numerator. We have something minus something, or a minus b, right? And then we have an a plus b. So our result should be a squared minus b squared, which will then, fix that square root there for us. Okay, and so we multiply there and we get x plus 1, and they're going to have a negative root x plus 1 and a positive root x plus 1 for the outer and inner terms there when we multiply them, which means they'll cancel. And then our last term is minus 1 times positive 1, so minus 1 all over. And then I'm going to leave the denominator undistributed here, and you'll see why in just a second. So don't distribute that x to the denominator. Because we can simplify some more, right? What simplifies here? What can we cancel out? What can we simplify here from this point? What's that? What can cancel? Nothing? Silence? What can we cancel here, folks? What cancels? What simplifies? We have x plus 1 minus 1 all over x parentheses root x plus 1 plus 1. What can we cancel here? The plus 1 and the minus 1. Yeah, the ones can cancel. Okay, there we go. We got the x over x root x plus 1 plus 1. Okay, and now it can cancel. The x's, that's right. What's left in the numerator when we cancel that x out from the numerator? A 1, yeah. Okay. Whew, that was a lot of work. Well, now we got something. What do you think we should maybe do from here? Substitute in the 0. 1 over root 0 plus 1 is, that's going to be root 1. Root 1 is 1, so 1 plus 1, that gives us 1 over 2. See? Instead of just like typing stuff in our calculator, we can take, like 1, 2, 3, 4 steps and get the same answer. Okay. The quiz, by the way, on Wednesday will be non-calculated, so keep that in mind. Okay, love it. I know, yeah, it's good. It's good. Okay. I like the attitude. Positive mental attitude. All right, so let's try another one. Okay, x minus 2 in the numerator, 3 minus the square root of x plus 7 in the denominator. We'll do one more here together, and then I'll have you guys try one. And then we'll get to that graph on the back. Okay? So, first step here, what do you think we should do? Ideas. What's that? Well, so we want to be careful here. Whatever we do, we want to not change the value. If I were to just try and like come in and square this, right, I would need to kind of like balance that out. So like I would, need to do that. So if I just come in and like square something, I would need to like square root something as well. So we'd be right back to where we were. So not quite that. So first of all, let me just say this, okay? Just because you see a square root, don't feel like you have to jump in and rationalize, okay? Now, obviously, because we're talking about rationalization here, I'm going to give you rationalization problems. But later on, right, when it's on the quiz, and this is part of the difficulty of the quiz too. I want to make sure that I take some time to help you guys appreciate that too, right? This might seem, very doable and like easy to you now. But remember, on the quiz, I'm not going to prompt you with like, for this question, use rationalization to answer it. You will need to be able to identify and diagnose what strategy to use when you come across a certain problem. Okay? Granted, when you see a square root, there's a very good chance you'll have to use this rationalization in order to, solve it. However, you should still try direct substitution because just because you see a square root doesn't mean the limit won't work right away. In this case, it doesn't though, right? 2 minus 2 is 0 in the numerator. 2 plus 7 is 9. Which square root of 9 is 3. 3 minus 3 is 0. You get 0 over 0. Okay? But you should still try it. Still try it just to make sure, because that can save you some time. Rationalizing something you don't need to rationalize. But in this case, we do. So, what do I want to multiply the top and the bottom by in this case? 3 plus root x plus 7. So the only sign that has to change is that, the 3 minus root x plus 7 to 3 plus root x plus 7. Don't feel like you need to make the x, plus 7 an x minus 7 or anything like that.
So
yes?
with the first one, we multiplied with the numerator. How come this one we're multiplying by the denominator?
So where is the square root? Where was the square root in the first one? Where was the square root in the second one?
So wherever the square root is.
It's because it's the square root that's kind of causing us the issues about simplifying, right? Because simplifying the square root is more tricky, more challenging. So if we can try and eliminate that square root by using this idea of like difference of squares and things, then we can maybe simplify it a little better. Okay? So, again, I'm not going to multiply out that numerator now in this case because we're hoping it's going to simplify for us. But the denominator I will multiply out. So again, first will be a 9. The outer and the inner, right, we have a positive 3 root x plus 7 and then a negative 3 root x plus 7. So that's going to cancel out. And so we have minus then the quantity x plus 7. Minus the quantity x plus 7, right? So that means, since we have a minus sign in front of parentheses here, that means that minus sign distributes, right? So we'll have minus x minus 7, so it'll be 2 minus x, right? 9 minus x will be a minus x, 9 and then the minus 7. So 9 minus 7 will be 2, positive 2. So 2 minus x. So can we cancel out x minus 2 and 2 minus x? Are they the same? No, right. We can't like switch around subtraction like you can addition and multiplication, right? 3 minus 2 is not the same thing as 2 minus 3, okay? Subtraction is not commutative. Addition is, right? 2 plus 3 is the same thing as 3 plus 2. Multiplication is 2 times 3 is the same thing as 3 times 2. but division and subtraction are not. So, are we done here then? Is that the best we can do? No, what can we still do from here? Can't get them to cancel with the way they're written. Any ideas? What? Yep, that's true. What we could do here, though, so this 2 minus x is almost identical to x minus 2, but it's exactly the opposite, right? Where we have a negative 2 here, we have a positive 2 here. We have a positive x here, we have a negative x here. So what we're going to do is factor a negative out of that denominator. Okay? When you have two things that like are so close to factoring, they're just opposites from each other, factor a negative out of one of those two things. I'm going to do it out of the bottom. But you could do it out of the top if you wanted to. It's your kind of choice there, right? So factor negative 1 out, and so that leaves us with a positive x minus 2. Right? Imagine redistributing that negative 1, negative x, positive 2. Oops, sorry, what's what we have right there? 2 minus x. Negative x, positive 2. Okay, x minus 2's cancel. And now the x minus 2's cancel, what do you think we can do now? Direct substitute now, exactly right. And so we'll get 2 plus 7, well, I'll go ahead and just do it here. 3 plus square root of 2 plus 7 over negative 1. So that's 2 plus 7, 9. Root 9 is 3. 3 plus 3 is 6, so it's negative 6 is our final answer there. Excuse me. So we get an answer, negative 6. Okay. Can we try another one? Absolutely, but this time I'm going to have you guys try this one on your own, okay? So, limit as x approaches 0 of the square root of x plus 9 minus 3 all over x. Go ahead and give that one a shot. I'll leave up the second one there too for you to look at. And I'll come around and help as necessary here. Don't forget to continue to write that limit. Okay? Until you have actually evaluated the limit, until you actually do the direct substitution there, you need to continue to write that limit as x approaches 0 in this case kind of thing. Doggone it. So multiply it out, right? So we have what is essentially a binomial. 1 minus, or so something minus 3, right? So like, 2 terms, and then here this is also 2 terms. So FOIL it out, right? So the first, when you do root x plus 9 times root x plus 9, it's going to be root x plus 9 squared, which is just then x plus 9. Well, so no, when you multiply this together, this times this, right, it'll be root x plus 9 squared. So you're multiplying it by itself, right, for the first terms. Okay, so you just have x plus 9. Then the outer terms, positive 3 root x plus 9, and the inner terms, negative 3 root x plus 9. So the outer and inner terms are going to cancel because they're exact opposites of each other. Right? You see that? You have 3 root x plus 9s and negative 3 root x plus 9s. And then the last term would be negative 3 plus 3, so negative 9, so minus 9. Okay. And then the bottom is And good, thank you for continuing to write the limit there too as you go. Yes? So continue to write the limit as x equals 0 because you haven't done that yet. Now you're going to substitute 0. Well, actually, I would simplify the numerator, right? The 9s will cancel, and the x and the x is eliminated. And then you can substitute in. So plus 3, yep. Correct, exactly right. Nope, it's positive, negative, we're trying to create a difference of squares. So whatever, if you have a plus b, then you need to multiply by a minus b. And then vice versa.
I will break your fingers.
Very good. Okay, good setup so far, yeah. That's right, not sure how to multiply from there though. Okay. So essentially it's like foil, right? So if I may, like that, right? So it's like a binomial. So first, it'll be these two, multiply together. This times this. Well, you're multiplying it by itself. So it's like root x plus 9 squared, right? Because it's multiplied by itself. When you square a square root, it becomes just x plus 9. And the outer term, positive 3, positive x plus 9, so you get positive 3 x plus 9. Well, then the inner term will be negative 3. Negative 3 x plus 9. So you have positive 3 x plus 9 and negative 3 x plus 9. They'll cancel out. The middle term goes away. And the last, negative 3 times 3 is better than 2. So it'll be x plus 9 minus 9. So just means
Did I do this?
yes. Yeah, no, that's right. So are you have further questions then, or because you did it right? Okay, that's it. We're gonna go. Okay. So these cancel with the x. The x cancels. So you have 1 over that, and don't forget you still have to calculate the limit x equals 0. So still write limit x equals 0 there. Yeah.
Really?
And so it's root the whole thing. Now though, you can do that. Now you go to so 0 plus 9 is 9. Root 9 is 3. 3 plus 3 is 6. So 1. Okay.
I don't remember.
So you want to multiply okay, so I would suggest, I think you're trying to skip 3 steps here. So multiply by the conjugate. So in other words, multiply this and this by root x plus 9 plus 3. I'll show you. Yes, yeah. Because you do negative 3 times positive 3, it should be negative 9. Yes, looking good, looking good. Good job, Mom. I think I saw everybody else then. 1 6. 1 6. Questions on any of this? Yes, Jen?
I'm done. Okay, I got it.
You got it okay?
Yeah.
All right, any questions on this one? All right, so again, we're multiplying by the conjugate here. The conjugate is root x plus 9 plus 3. Okay, it's from the numerator there. We want to get rid of that square root. Again, square roots, it's ideally, for simplification's sake, we want to get rid of them, right, if we can. Especially when you have like a root of, a sum kind of thing. Those are hard to simplify. So we get rid of them by creating a difference of squares. We multiply a minus b times a plus b. Results in x plus 9 minus 9 all over x, and I didn't multiply the bottom out. I didn't multiply the numerator out. I just multiplied the numerator back. I didn't multiply the denominator out. I left that unmultiplied. But the numerator we did multiply out there, right? To get that to work. Okay, so we ended with x plus 9 minus 9, which leaves you with x, but the x's then can cancel, leaving you with a 1. Plug in the 0 for x, and then voila, you get 1/6. Okay? So, questions? Any further questions on that? All right. So let's turn our papers over then. We'll get some more practice with this for the homework here too. But let's turn our papers over because I do want to talk about evaluating limits graphically. Okay, I capitalized a bunch of things here, don't know why. Anywho, okay. So we'll say this is our function right here, f of x. The whole thing is our function. So it's probably a piecewise, right? Because you have a bunch of like weird pieces here. You have like a line, you have a point, we have like what looks like part of a quadratic probably here, and then what looks like part of like a rational function like 1 over x or something like that. Of course with some transformations and things. All right, so the whole thing here taken together, okay, is f of x. So we'll just take a look at evaluating some of these limits that I'm going to come up with here for us. So limit as x approaches -2 of f of x. Okay. So as x approaches, in other words, what this is saying is as x approaches -2, what does the value of our function approach? Okay. So what do you say? 3. Okay. Yes, it's 3. Okay. As x approaches -2, so there's x equals -2. Okay. As we approach -2 from the left-hand side, we're going to be moving along this part of our graph. As we approach -2 from the right-hand side, we're going to be moving along this part of our graph. And both of these kind of come together at a point at 3. And so, yes, the limit as x approaches -2 of f of x is 3 here. But what is f precisely at -2? What is the value of the function precisely at -2 going to be? It is 4. Right, 4, okay? Because precisely at -2, we're going to go up, up. It's a hole. We keep going. 4 is where we have an actual value there, at -2. But approaching x equals -2 from the left or from the right, they both are going to go and lead towards 3. Okay? So, let's try another one here. Let's do the limit as x approaches 1 of f of x here. So locate where x is equal to 1 on your function. Okay, so there's where x equals 1, right? But of course we're trying to approach 1. So we're going to follow from the left-hand side, to the left of 1, our graph is this part of the graph right here, like that parabola kind of thing. And to the right of x equals 1, our graph is like this rational function piece. So from the left, what value does it look like our function's approaching? 0. And from the right, as we approach in towards that 1, what value does it look like our function is approaching? 0 as well. Aha! From the left and the right, it's both 0, so we'll say 0. Okay. And of course, I'll ask a similar kind of question here. What is f exactly at 1? What is the value of the function exactly when x is 1? It is 0. Yeah, it's a 0. There's a point there, right? At 1, point, 0. Okay, so that's it.
Why is 3 0?
Why is 3 0?
You have number 3.
Oh, number 3. Gotcha. Yeah. So we're approaching 1, right? As x approaches 1. So here's 1. Okay. As we approach 1 from the left, right, from values less than 1, we're going to be on this part of the graph. Right? As we get closer and closer and closer to 1, what's the y value we're approaching here? 0, right?
Okay.
And then as we approach 1 from the left, this is going to be this part of the graph we're going to use to approach 1 from the left. And as we get closer and closer and closer to that x value of 1, what y value are we approaching? 0. That's the idea. Okay. All right, number 5. The limit as x approaches 3 of f of x. Whoops. Okay, so now we want to approach the x value of 3. All right, so here's the x value of 3. Okay, if we approach 3 from the left-hand side, we're going to be on this part of the graph, right? This part of the graph right here. Okay. As we approach 3 from that left-hand side, what's the y value or the function value look like that we're approaching? Yeah, probably negative infinity. Okay, it looks like that. And as we approach 3 from the right-hand side, we're going to be on this part of the graph. And what does the y value look like we're approaching there? Okay, so we're approaching negative infinity from the left, positive infinity from the right. So we'll say the limit then, what? Does not exist. Exactly right. Just like Lindsay Lohan said at the end of Mean Girls, the limit does not exist. Okay? Yeah. Limit does not exist. Limit does not exist. Usually just like that. What she does, though, is a completely different limit than what we're doing right now. You need calculus to do the limit that she was doing. You have to use L'Hopital's. But yes. I don't know. I feel like as the years goes on, that reference is probably going to become like less and less relevant because the movie's going to be older and older, and eventually people won't watch it anymore. And yeah, it's a little sad. It's a little sad. But I think it'll still probably be appropriate. It just won't be I think it'll be like, to me, what like Pretty in Pink and like The Breakfast Club are. It'll be like those like, oh, those like cool like older movies that deal with like high school and stuff. But like no one really watches them now anymore. Like we've got, I don't know. I guess when it was like High School Musical was like the new stuff that people would watch. It was dealing with high school and all that. But anyway, and you guys probably watch like Riverdale now or something, which is just like stuff from like the 50s, but then they brought it forward with the character names and all that. Anyway, who knows? Maybe they'll remake Mean Girls or something like that with some new girl. And anyway,
They're remaking it into a TV show, and they already have a musical.
that's true. Oh, I didn't know it was a musical or a TV show. I mean, that's interesting. The musical I heard about. Anyway, yeah. I saw the teaser trailer, yes. There was like nothing to it, but yeah, it's going to be interesting. Yes, there's no new ideas. We just remake the old ones now. We've run out, Just like, let's just recycle the things we've had. So anyway, yes, that's Toy Story 4, yeah. It's going to be interesting. I don't know. Supposedly I don't know. We'll see. Anyway, so f of 3, what's the value of f at 3? Precisely at 3, what do you think the value is? Yeah, it does not exist either here, okay? We don't know. Because there's no point there, right? Because we have a vertical asymptote. Okay? So, what's the purpose? Why do we go through this, right? Well, the point of this, or kind of the thing I want to kind of stress, is that the existence or non-existence, okay, of f of x at a particular value, okay? So whether a function value exists at a particular value, c for example, has no bearing, okay, on the existence or non-existence of the limit. Non-existence. I lost there. I did write a C there, but it's kind of all right. Whatever. I'll just rewrite the whole thing. Non-existence. There you go. Of the limit as x approaches c of f of x. Okay. The existence or non-existence of a function. Okay. Whether a function has a value or does not have a value. Okay. At a particular x. Or like c, for example, x equals c. Has no bearing on the existence or non-existence of the limit as x approaches c of f of x. Okay? Unless the function is continuous, right? If the function is continuous, which is what we talked about earlier, then the limit and the function are the same value, must be the same value, right? So if a function is continuous, the limit as x approaches c of f of x is f of c, but only if the function is continuous. Here, is this function continuous? No, and so you can see that relationship breaks down between the limit and then the value of the function. They don't have to be the same thing. Right here, the limit as x approaches -2 was 3. The value of the function at -2 was 4. Here, at 1, they did agree, and which makes sense because at 1, is the function continuous at 1? Yeah, right around there, it's no problem. And then at 5, they both do not exist, okay? But kind of, for different reasons. There's no value at 3 for that one, and this one, they're going to negative infinity and positive infinity. Okay? So that's the idea here.
So would you write at the end of that unless it's continuous?
Yeah, you could say that if you wanted to. Might not be a bad note there. Yes, unless f is continuous. Okay, unless f is continuous. Then the value of the function and the limit as x approaches, that particular c value, they are the same thing. All right, I've got one more thing I'm supposed to show you here, so I'm going to do that. All right, I know we're kind of running low on time, but I want to get through this because I don't want to just push it off till tomorrow. Well, let me see what tomorrow looks like just in case. better to do it now and just have it done. Okay, so the last thing we're going to look at here are limits at infinity. Okay, in other words, the limit as x approaches positive infinity of f of x, or the limit as x approaches negative infinity of f of x. Okay. Now, we've already kind of been doing this. If x is approaching positive infinity, that means we're trying to figure out what happens as x goes really, really far to the right? As our function goes really, really far to the right. Or if x is approaching negative infinity, that means we're really trying to figure out here what happens to our function as x goes really, really far to the left. Okay? Now, what have we already kind of been talking about in regards to what happens to our function as we go really, really far to the right, or what happens to our function as we go really, really far to the left? We called that what? End behavior. Yes, this is merely end behavior. Okay? It's merely end behavior. Okay? So, we can still use that idea of end behavior. In fact, we were kind of doing limits when we talked about end behavior, right? We said as x approaches infinity, f of x approaches positive or negative infinity, right? Kind of thing. That was a limit, right? We were kind of using that concept, but without saying it expressly. We're going to talk about guidelines for evaluating limits at infinity of rational functions. Okay, we already know how to do it with polynomials, right? You just look at the degree and the lead coefficient, right? You can do that. But for rational functions where you have like, something, a polynomial over a polynomial, 3 different scenarios, okay? If the degree of the numerator is greater than the degree of the denominator, okay? So if your numerator has a greater degree than your denominator, we're going to say the result there is that either the limit as x approaches infinity of f of x, or limit as x approaches negative infinity, right? Either one will be does not exist. Okay. Why is that? What's happening? Well, we'll get to that. I'll explain it to you when we get to an actual example. All right. And if the degree of the numerator is the same as the degree of the denominator, okay, if the degree of the numerator is equal to the degree of the denominator, what does that mean? That means the limit as x approaches, bless you, positive or negative infinity, I'm just going to write both here, of f of x, would be the ratio of the lead coefficients. Okay. And then finally, number 3, the last possibility, right? So either the numerator will be greater, the numerator will be equal, or the degree of the numerator will be less than the degree of the denominator. Okay? And in that case, the limit as x approaches positive or negative infinity of f of x will be 0. Okay? And I'll do 3 quick examples here and talk about why that is. Okay, so we'll just say evaluate, squeeze it in here at the bottom. Should have enough room. Okay, so like I said, we're going to do 3 examples here. We'll talk about all these. I'll go ahead and just write them all out here. And yes, our 3 examples will correspond to the 3 different scenarios there. Not surprising. Say again. 3x squared, yes, both in 1 and in 2. In the denominator, it's 3x squared. Uh-huh. Uh-huh. Okay. So. These are all limits as x approaches infinity. Okay. So, what's happening here, right? So, imagine trying to do a direct substitution with infinity. Okay, now obviously infinity is not quite the same as every other number, but it still is a number, right? It has value to it, and so we can kind of like imagine this here. So imagine trying to do a direct substitution here with infinity. We're going to take that number infinity, we're going to plug it in for our x's, both in the numerator and in the denominator here. Okay, now, in the numerator, we're going to take that infinity, multiply it by 2, okay, so it's like going to get a little bit bigger, right? And we're going to add 5, which again is going to get a little bit bigger. But really taking infinity, multiplying by 2, and adding 5, okay, it's still going to be infinity, so that's that. Compare that to the denominator here. We're going to take infinity and square it. Infinity times infinity, then times 3, then add 1 to it. The infinity on the bottom is going to grow or increase in value at a much faster rate. Why? It's being squared, right? Since the denominator, okay, its growth, its value is going to vastly outpace the numerator's growth, okay? Even though infinity keeps going, the denominator is going to keep going faster than the numerator will. And so what that means is, well, what happens to the value of something as its denominator gets larger and larger and larger in comparison to the numerator? What happens to the overall value? It goes to what? It gets less and less and less and decreases to what, though? To zero, right? To no value, right? If you have a large denominator, like, right, 1 over 1,000,000, 1 over 1,000,000,000, 1 over 1,000,000,000,000, right? Those are getting closer and closer to 0. And so that's why, since the degree of the denominator is bigger, we go to 0 there. Okay? The numerator has a smaller degree than the denominator. The denominator gets bigger faster. Okay? Number 2, in this case, both infinities in the numerator and denominator will be squared. So they're both going to be squared, so that means they're going to kind of maintain that same growth, I guess I'll say. Yes, there's a 2 in the numerator and a 3 in the denominator, and that's going to matter here. But essentially, because they're both being squared, they're both kind of going to grow at the same rate. And so as they keep growing, they're going to kind of, cancel one another out because they're the same and leave you behind with just the 2 and the 3 there, the 2/3. The plus 5 and the plus 1, they're going to be negligible, right? Because when you're talking about very large numbers, adding 5 to a very large number, adding 1 to a very large number, doesn't really matter. But they'll cancel out, and then we'll be left with just the 2/3 there, the ratio of the lead coefficients. Again, why? Numerator and denominator the same degree, right? So it's just the 2 and the 3 there. Okay. Excuse me. And last but not least, number 3, in this case, which part's going to get bigger faster, the numerator or the denominator? Numerator, because why? We're going to be cubing infinity. Now, what happens to the value of a fraction if your numerator gets bigger faster than your denominator? It gets bigger and bigger and bigger, goes to infinity, so we'll say the limit does not exist. Okay? Anytime you have a limit that goes to positive or negative infinity, we say the limit does not exist because, by definition, a limit should be limited, not unlimited, right? It should be finite, not infinite. And so that's why we say it doesn't exist. Okay. Your homework is posted to Google Classroom. I'll see if I can pull it up here for you real quick so you can copy it down if you want to. Sorry for pushing things so close, but here we are. I'm going to put it on my stool there. Thanks, Mr. Dog.